Good evening, everyone. I'm Yashashvi Srivastava, roll number 18ME31030, the Department of Mechanical Engineering, IIT Kharagpur, and I'm undertaking a project on the design of electro-pneumatic hydraulic variable valve actuator for a camless engine under the supervision of Dr. Dhananjay Kumar Srivastava. We generally make use of a camshaft so as to control our valve opening and closing times. These valve opening and closing times remain fixed and are very often not optimized to the persisting road conditions. For example, let us assume that our camshaft has been optimized for a certain speed. However, due to the traffic conditions, the speed of the vehicle is not the same as the speed at which it has been optimized. This results in a very inefficient process in terms of fuel consumption and operating characteristics. So the variable valve actuation is a major interest area for research in internal combustion engine since it is aimed to give a greater degree of freedom to optimize the opening and closing times of the intake and exhaust valves. Variable valve actuator systems are of two types: cam-based and camless systems. So types of cam-based systems are cam switching, cam phasing, and multi-cam systems. On the other hand, the types of camless systems are divided on the basis of their working principle. So there are electro-hydraulic VVA systems, electromagnetic and electro-pneumatic VVA systems, where VVA stands for variable valve actuation. The working principle and the components of camless VVA systems also cause some issues to exist due to their physical properties. There is noticeable complexity in the managing strategy of VVA systems since these systems generally have a fixed rise and lift times. In order to achieve this, we have to deactivate some of the cylinders or valves in order to adjust to the varying load. The camless VVA strategies and their management system need to be of a very good level of safety and reliability, and for that they need to be robust. So we are here to present electro-pneumatic hydraulic variable valve actuator as an alternative to solve the problems of the other camless VVA systems. Some of the challenges in electromagnetic systems are non-linearities in electromagnetic forces, which lead to high level of noise and coil inductance, cause time delays which gives worse or poor actuator response. The actuator response can be greatly reduced in electro-hydraulic systems by the oil in the hydraulic circuit. However, the response of the system is slow at low lifts. This in turn is counteracted by the electro-pneumatic system, which gives faster response of actuation. So let us discuss the viability of EPH VVA. Combining the benefits of both hydraulic and pneumatic system, we can have a better system which has a faster response, better control over part lift operations and low seating velocity. Such system consists of both hydraulic and a pneumatic circuit. The pressurized air provides necessary actuation force, and the pressurized oil serves the function of hydraulic latching at part lifts and hydraulic damping for controlling seating velocity. So in the project, we designed a SolidWorks model of the proposed EPH VVA, and it is as follows. So this is the assembled view of the EPH VVA, and this is the exploded view. This is the top part and has the valve opening for the pressurized oil to enter. This is the piston, and it goes up and down for actuating the valve opening and closing. This is a spring to send the piston back up when the time arrives. This is the main body and contains the valves 1 and 3 for the pressurized air. This is the bottom cap of the assembly, and this is the valve. So this is assembly and explosion of the EPH VVA system designed. These are the various components and how they are fitted together in the proposed system. It has been designed on SolidWorks. So moving on to the working of the EPH VBA. This is the proposed working and has been broken down into four possible stages: the initial stage, the charging stage, dwell stage, and the closing stage. So at the initial stage, we are going to say that the intake exhaust valve is at an extreme position, resulting in the valve being closed. At this position, all the control valves are in closed position. Now, in the charging state, the electronically controlled valves 1 and 2 open, resulting in pressurized air entering the pneumatic circuit and pushing the actuator piston. The actuator piston starts compressing the spring and the intake exhaust valve is opened. Pressurized oil is filling the hydraulic circuit at this stage. Moving on to the dwell stage, now both valve 1 and 2 are closed. Once there is sufficient pressurized air so as to provide the necessary lift, the oil that has entered holds the piston at the desired position and stops it from moving backwards throughout the dwell stage. Once it is time to close the intake and exhaust valve, the valves 2 and 3 are opened and the spring depressurizes the circuit. The oil causes hydraulic damping and prevents the valve from hitting the actuator with too much force and thus prevents damage to it. This hydraulic damping is in addition to the benefits of hydraulic latching which has been provided by the oil. After the closing stage, we again revert to the initial stage for the next round or valve event. So in the further course of action and what we intend to do in the future, so the dimensions for our product have the constraint of space, and we will have to choose appropriate dimensioning for it. After we have made the actuator system, we can move on to designing the hydraulic and pneumatic circuitry for the system based on our specific performance requirements. Once these preliminary design and circuits are ready, we can use a suitable simulation software like ANSYS in order to simulate the performance of our VBA. We would be meanwhile exploring the available production and manufacturing methods for manufacturing the prototype for the developed model.